It's Pi Day! This is Maggie from Design Code Debug Repeat. Welcome to the channel. Today is March 14th, which is Pi Day, at least in the US, where our dates are inexplicably written month first. But I welcome you, no matter where you live, to celebrate with me as I explore two of the ways that pi has been approximated historically. We'll look at a couple of Python programs that calculate and illustrate these approximations, because a .py program seems a very fitting way to approximate pi. First, what is pi and why do we care? To understand pi, start by thinking about a circle. I'll bet you have a clear image in your mind. Now let me ask you a slightly trickier question. How do you define a circle? Mathematicians define a circle as the set of points that are equidistant from a center point. So, in other words, pick a point and a length, which you can call a radius, and stick one end of your radius at that center point, and a circle is all of the points that are touched by the other end of that radius. This is how we draw an accurate circle with a compass. If you then take that radius and double it, you can fit approximately 3 of those doubled radii around the edge or circumference of your circle. The exact number you can fit around is pi, 3.14159, etc., no matter what size your radius or circle. This is a proportional relationship. The circumference of the circle is always 2 pi radii. The constant pi captures our attention, I think, first because it does not repeat. Over 200 trillion digits of pi have been calculated, and in those 200 trillion digits, there is no repetition. It's also fascinating because it is a constant. No matter what size circle we have, the ratio of the radius of the circle to its circumference will be 2 pi. And finally, because we love to celebrate, and the Greek letter pi sounds like the dessert category pie, which usually comes in circle shape. It's a holiday with a delicious, authentic, built-in way to celebrate. So, grab your favorite slice of pie, and let's get started. People have been approximating pi since around the 20th century before the Common Era, maybe even earlier, but we'll start with an algorithm based on Archimedes' method of inscribed polygons, developed in the 3rd century BCE. Archimedes inscribed a polygon within a circle, and circumscribed a polygon outside the circle, then used the perimeters of the polygons to approximate pi. This provided upper and lower bounds for pi. We'll look at how you use an inscribed polygon to approximate pi using trigonometry, which Archimedes did not have. I'm going to illustrate this with a square, simply because a square is such a simple shape with simple angles that I think it is easy to understand. Here I have a circle with a square inscribed within. If I draw radii from the corners of the square to the center of both the circle and the square, I form 4 triangles. Each of these triangles will have an angle at the center, which is 2 pi over 4 radians. If you're more comfortable with degrees, that is 360 over 4 degrees, or 90 degrees. We're dividing by 4 because that is the number of equal angles we've divided our circle into, the number of sides of our polygon. When we generalize this algorithm, we'll use the variable n for the number of sides instead of 4. Now, if I bisect that angle, I'll have a right triangle, and then I can use my trigonometry. My angle at the center is now pi over 4 degrees, and the hypotenuse is the radius of the circle. Remember your SOHCAHTOA, the sine of an angle is the opposite side over the hypotenuse. So the sine of pi over 4 is opposite over radius. With a little algebra, I get the length of opposite is radius times the sine of pi over 4. That's half the length of a side. If I want to know the full perimeter, I'll multiply that by 2 to get the full length of a side, and then I'll multiply that by 4, the number of sides. Let's write that out generally now for any size polygon. Instead of writing pi over 4, where 4 is the number of sides, I'll write pi over n for the number of sides, and instead of multiplying the side length by 4, I'll multiply by n, the number of sides. So I have the perimeter of the polygon for any polygon is 2 times n times r times the sine of pi over n. Now, how do we use that to approximate pi? We are saying that the perimeter of our polygon is an approximation of the circumference of the circle. So we'll set them equal, getting 2 times pi times r equals 2 times r times n times sine of pi over n. I can divide each side by 2r, isolating pi, and setting it equal to n sine of pi over n. That's it. That's my approximation formula. Let's plug in 4 for our square, and we get 2.82842, etc. Not a great approximation, but the more polygon sides we add, the closer our shape is to a circle, and the better our approximation. Archimedes went as high as a 96-sided polygon. Let's look at a program that calculates closer and closer approximations to pi with polygons with more and more sides. This is it, called Inscribed polygon.py. I'll run it first. The program starts with a hexagon, which you can see inscribed in the circle. And I urge you, if you're interested in this, to go through the calculations with the hexagon that I went through with the square, so you understand how our formula is derived. This gives us an approximation of 3, already closer than our square approximation. Now, each time I click, we get a polygon with more sides and an approximation of pi that's a little closer to the value we're familiar with. This program will increase the number of sides of the polygon up to 100. Let's take a look at the code. We start with drawing the polygon inscribed in the circle, which calculates the points at the vertices and passes them to pygame's drawPolygon function. This algorithm is possibly the more interesting one in the program, since we already know how simple the formula is for approximating pi based on the number of sides of the polygon. So let's take a look at how we're calculating the points. We start by calculating an angle called angle step. That's 2 pi divided by the number of sides, the angle we got when we split our square up into 4 pieces. Let's illustrate this algorithm with the hexagon, so that angle will be 360 divided by 6, or 60 degrees, or in radians, 2 pi divided by 6, or pi over 3 radians. We'll then iterate n times, in our example, 6 times, and create x, y coordinates for each vertex. We begin at 0. The x-coordinate is r cos 0, and the y-coordinate is r sine 0, again, according to SOHCAHTOA. It's easier to see that at the next angle. We then multiply I, now 1, by our angle, which will be 60 for the hexagon, and again calculate the x, y coordinates and store them in our list. When we're at 60 degrees, it's easy to draw the right triangle and see that the side opposite the 60-degree angle is the y component of the coordinate, and the side adjacent to the 60-degree angle is the x component of our coordinate. We're adding the center of the circle to our lengths as an offset. We want our polygon centered within the circle and in our window. We're not starting from coordinate 0, 0, which is the top left of the screen. So this calculates the coordinates for all 6 vertices and then passes them to drawPolygon, which will connect each set of points with a line. The function inscribed polygon pi calculates the approximation of pi based on the number of sides of the polygon. You can see it's one simple line, the formula we derived, n, the number of sides, times the sine of pi over the number of sides. That's it. You don't have to draw the inscribed polygon to approximate pi with this formula. Suppose we want to imagine a 1,000-sided polygon. In the console, I can import math, and then type 1,000 times math.sine math.pi divided by 1,000, and I get an approximation that's accurate to the 10,000th place. My program draws the polygon just as an illustration. The second approximation method we're going to look at is called the Monte Carlo method. It's named after the Monte Carlo casino in Monaco, as it relies on randomness and probability, much like games of chance in a casino. To understand how this works, imagine a circle inscribed within a square. The radius of the circle is r, which is half the side of the square. The side of the square is 2 times r. We will use the areas of the square and circle for our approximation. Let's look at how we do that algebraically first. The area of the circle is pi r squared, and the area of the square is 4r squared. If we divide the area of the circle by the area of the square and multiply by 4, we get pi. So we can approximate pi by taking the area of a circle, dividing by the area of the square, and multiplying by 4. But how do we get those areas? Instead of calculating them directly, the Monte Carlo method approximates them using probability. We generate random points within the square and count how many are inside the circle. Since the points are randomly distributed, the fraction that are inside the circle should be approximately equal to the ratio of the circle's area to the square's area. The more points we generate, the closer our estimate gets to the true value of pi, as randomness evens out over large samples. This method of using random sampling to solve complex problems was developed by the physicist Stanislaw Ulam and John von Neumann in the 1940s. Since then, the Monte Carlo method has been widely used in fields such as physics, finance, and artificial intelligence to estimate solutions to complex problems involving randomness and uncertainty. Shall we look at the code? I've implemented this with Python and pygame, and you can see the program running here. The number of samples is the number of random values generated. I can increase or decrease that with the arrow keys. And every time I click, the program will generate a new set of random numbers. I found that the approximation gets a lot closer to pi when I go up to 5,000 samples. And it is a lot more variable when I go down to 100 samples. In the program, I have a game loop in which I process quit, mouse, and key events. Let's focus on the Monte Carlo code, which is in the approximate pi Monte Carlo function. I'm using a unit circle, which means a circle with radius 1, centered at the origin. That means I'll be generating random x and y coordinates between -1 and 1. Some of those coordinates will fall inside the circle, and others will be in the square bounded by the points -1, -1, and 1, 1, but outside the circle. In the program, we are using random.uniform to generate random numbers between -1 and 1. This generates floating point numbers, with each number in the range having an equal probability of being generated. We then check if the point falls within the circle with if x squared plus y squared is less than or equal to 1, and if it does fall within the circle, we increment a count of points within the circle called inside, and we append to our list of points the x and y coordinates and true, meaning the point is in the circle. If not, then we do not increment our count of points inside the circle, and we append to our list of points the tuple x, y, and false, meaning the point is not in the circle. This list is for drawing the points, used by the draw Monte Carlo function, and we include true or false so we can draw the points within the circle a different color from the points outside the circle. Once we've generated all of the points, we can calculate our approximation of pi using the formula we derived earlier from the area formulae, 4 times inside, our count of points within the circle, divided by num samples, the total number of points we generated. We also return the list of points so they can be passed to the draw Monte Carlo function, which draws the square, the circle, and our red and blue points. That function is pretty straightforward. It iterates over the point tuples and draws them in blue if the Boolean is true, and red if the Boolean is false. Both of these programs are in my GitHub repository with a link in the description if you're interested in looking more closely at them. Aren't these approximations fun? Did you prefer one over the other? Tell me in the comments. There are many other methods for approximating pi, such as the WWII-Leibniz series, which is one of my favorites to assign to students who are learning to design loops, but I don't think it's quite as fun to illustrate as the two I've shown here. Maybe next March 14th I'll focus on loop design and the WWII-Leibniz series. Until then, I hope you'll come back for other programming videos and that you have a wonderful Pi Day. As always, have fun and keep coding.